Okay, welcome everybody. We're ready to go, I think. I left myself a very easy job. I've basically done it by saying welcome everybody. I would just also add that welcome to this Harry Massey lecture is hosted by the Department of Physics and Astronomy and the London Centre for Technology and held in the Chemistry Auditorium, just to give you a true flavour of the interdisciplinary nature of this institution. I'd like to welcome you all. Welcome our distinguished visitor, Professor Chu, but I'm going to hand over to Alexandra Olea Castro, who is the organizer of this seminar series, to give a more detailed introduction.
First of all, I would like to thank everyone who is in this auditorium and the other two auditoriums for attending our 2014 UCL Harry Massey lecture. Today, we are honored to have a speaker who is currently a professor of physics and professor of molecular and cellular physiology at Stanford University. His scientific career started flourishing at Bell Labs, where he was heading the group of quantum electronics for about 9 years, and then he moved to Stanford. While at Stanford, he made exceptional contributions to the science of atomic and molecular physics. In particular, his work on laser cooling of multi-level atoms and the demonstration of the atomic Fontaine clock made him the co-recipient of the Nobel Prize in Physics in 1997. His work has passed the boundaries of physics to make an impact in biology and medicine, where he introduced methods to simultaneously visualize and manipulate single biomolecules. In 2004, he moved to Berkeley, and he became the director of the laboratory, Lawrence Berkeley National Laboratory, and he stayed there until 2009, when he stepped down to join the cabinet of President Barack Obama to become the USA Secretary of Energy. He then became the first scientist to ever head a Department of Energy in the United States until 2013, April last year. During his time as head of the Department of Energy, he began several initiatives towards gathering resources and scientists who will think about how to solve the problem of energy that today the world faces. Part of these initiatives are, because these ones I don't remember them by heart, the energy ministerial meetings, the energy innovation hubs, the Anti-Advanced Research Projects Agency Energy, known as ARPA-E, which will focus on research leading to really disrupting technologies that could help us solve that problem. Today, he's going to share with us his experiences by telling us about energy and climate change challenges and opportunities. Please, let's welcome Professor Steven Chu.
Thank you for this kind introduction. And so without further ado, let me begin. And again, I apologize for being late. We were having a lunchtime conversation and lost track of the time, which is, I guess, good news because it was interesting. In any case, let me talk a little bit about how innovations really change the world. And these are innovations in science, in technology. And of course, one of the biggest innovations was the beginning of the Industrial Revolution. One of my favorite paintings and painter, Turner, here you have a picture of a coal-burning, steam-powered tugboat towing an iconic warship to its final berthing, where it would be broken up for scrap. And here you have really the changing of the guard, the setting of a sun of a romantic sailing era, if you will, and the beginning of steam-powered boats and trains and everything else. And so this really began to transform the world. There were other innovations that transformed the world in agriculture. For example, Sir William Crookes, when he was being inaugurated as the president of the British Association for the Advancement of Science, in his inaugural speech, instead of using the usual, "I'm so glad to be here and thank you for this great honor," he started off by saying, "England and all civilized countries are in deadly peril." This is not your usual inaugural speech. he goes on to say, it's the chemist who must come to the rescue. And before the actual grip of mass starvation, what was the issue? The issue was that rotating crops weren't enough to keep the agriculture going. They were starting to use artificial fertilizers. They found that bird guano, bird doo-doo, was a great fertilizer, but then they were importing this from South America, and that was soon being depleted, and then they went to Chilean saltpeter. Again, nitrogen compounds, which was great. But then he did this little calculation, said, you know, in about 20 or 30 years, the way we're dipping into the saltpeter reserves, we're going to run out of this as well. And not only England, but all of Europe. And so he set, in his inaugural speech, a sort of a race, if you will. Can you develop artificial nitrogen-based fertilizer? And it very quickly was an issue whether you can do this and can you synthesize ammonia in some way. And in the end, Fritz Haber was able to catalytically make ammonia. He did it in collaboration with Carl Bosch. And for that work in 1918, he was awarded the Nobel Prize in Chemistry. Remarkably, Carl Bosch then got another Nobel Prize for essentially the same work. They made up another reason. They called it high temperature, high pressure catalysis, but it was actually high temperature, high pressure in the 1918 one. But it shows you how important it was to be able to make artificial fertilizer. And finally, in 2007, when we're starting to learn more about catalysis, and Gerhard Ertl got the Nobel Prize in Chemistry, it said in the citation, at last we're beginning to understand at a microscopic point of view the Haber-Bosch process. So 2.5 Nobel Prizes, because it was a big deal. And so because of that, at the beginning of the Industrial Revolution, where there were 700 million people, this enabled Europe to feed itself. And this continued and was successful. But by the 1950s and 1960s, the population of the world was still expanding rapidly. And a professor at Stanford, Paul Ehrlich, said in a best-selling book called The Population Bomb, he said, the battle to feed all humanity is over. In the 1970s and 1980s, hundreds of millions of people will starve to death in spite of any crash programs embarked upon now. And so he wrote this book. It came out in 1968. And you might ask, what happened? And so what happened was there was another revolution, not an industrial revolution, but a green revolution, spearheaded by Norman Borlaug, who bred many strains of wheat to produce a dwarf strain of wheat that had much larger grain sizes, as you see in this picture over here, that the dwarf strains of wheat were much more productive. In fact, the wheat kernels were so heavy, he hybridizes to make very short grains of wheat, so the gravity would just not pull the plant over. He also made them tolerate artificial fertilizers, which are put in the soils very suddenly. And so you could use artificial fertilizers more productively and increase productivity. So here is what we see in terms of 1960, and population bomb is produced here in 1968. And this is the amount of land put under agricultural cultivation from 1960 to 2005, and the population of the world more than doubled. This is the amount of grain production. This is wheat, this is corn, rice. And what you find is that around the world, on a per acre basis, the production went up about fourfold per acre. And so the amount of land put under agricultural production actually remained relatively constant. So these were cereals that were the main food stay, if you will, of the world population. And so it's remarkable. But now we know that we actually need a second green revolution, that if it's possible to transition instead of annual crops to perennial crops with very little tillage. Fertilization is a problem, and there's a tendency to sadly to over-fertilize because fertilizer is so inexpensive, and that leads to a lot of water pollution issues. There are lots of things. But nevertheless, this was an important development. So let me turn to another technological development that certainly transformed the world, and that is the automobile. But it's not just the automobile. It was Henry Ford's vision of an automobile that would be much less expensive than the type of automobiles made by Benz in Germany, by Peugeot in France. So these would be automobiles that many citizens could afford. And he really wanted to drop the price dramatically. And his vision was that if you could drop the price, it could be something not as a luxury item, but something that could have deep market penetration. He started several companies. The first one in 1899 went bankrupt. 1901 company didn't go bankrupt, but Henry Ford was a kind of, the technical word is he was a control freak, and he didn't want any other person in the company to have anything to do with engineering. And so when the investors hired another engineer, he quit in a huff and started a third company. But now still looking for investors because this is not a good track record. This is company number 3, and what's this guy about? And he's kind of had strong opinions. And so he had a lawyer, and he asked his lawyer, would you invest in this new company? The lawyer asked the president of Michigan Savings Bank, should I do this? And the president of Michigan Savings Bank said, the horse is here to stay, but the automobile is only a novelty, a fad, and it will pass. Now luckily, his lawyer did not follow his advice. He invested $5,000 in 1903. That's worth a lot more than you have to slide the decimal point over at least one, possibly 2 times. But he later sold stock for $12.5 million. So that worked very well. If you think about it, the transition from horses and horse-drawn carriages to automobiles, considering all the infrastructure needs, you needed better roads, you needed liquid hydrocarbon transportation fuel, gasoline or diesel. And if you consider how fast that went from the 1990s, here's a picture of horse-drawn carriage in New York City, but by 1920s, you can see a rapid displacement of horses for automobiles. And so here you see virtually no horses and a few electric trolley cars, but now rapidly converting to automobiles. So it was technologically better, but it wasn't obvious in those early years that it was technologically better, and there were a lot of detractors who thought that automobiles were inherently dangerous. You're driving with this liquid transportation fuel. It could be essentially a bomb, et cetera, et cetera. But there was another thing that hastened the conversion to automobiles, especially in large cities, and that was an environmental issue. There was a pollution issue. And what was the pollution issue? Well, in New York City and Brooklyn, there are 160,000 horses. They were producing 3 to 4 million pounds of horse manure a day and 40,000 gallons of urine a day. And the horse manure was piling up rapidly in all the vacant lots in Manhattan. There were vacant lots in those days, and going 1 story high. It was so thick in horse manure that young entrepreneurs, kids, would then have brooms, and they would offer their services to well-heeled pedestrians that they would sweep the street, a little pathway, so they can walk across the street without getting ankle-deep in horse manure. So it was pollution that was very visible, couldn't help but be noticed, and it was this pollution that really helped accelerate the transition. Needless to say, the fertilizer market was saturated. So it was going. So now we have some pollution of another kind, and that is, of course, that we have, well, there's very standard types of pollution of SOx and NOx and other things, but there is also evidence that the climate is changing. And so this is the temperature record from 1800 to 2011. of the land average temperature. And you see, first of all, let me just point out that we don't understand these plateaus and even dips, and there's a local plateau of about 10 years or so currently. So we don't understand that. We don't understand these spikes. So there's a lot of aspects of climate change that the climate modelers are still working on. But nevertheless, if you just look over a period of 200 years, what you see is that temperature is increasing, number one. Number two, most of the increase has been over the last 35 years or so, and the most recent IPCC has now up, they did a slight adjustment, so it's now believed to have been about 0.85 degrees since 1880, the increase in temperature. So the temperature, the average temperature of the Earth has been increasing. This is something that many scientists have noted. Surprisingly, in Washington, D.C., it's still a contention of debate as to whether something is happening. But it is increasing, and the ocean levels averaged over around the world have been going up. I want you to focus on the fact that the land temperature has increased dramatically more than the ocean temperature, and I'll get back to that. And the ice masses in Greenland and Antarctica over this decade, 92 to 2001, this is the loss in ice mass, and in the subsequent decade, there's significantly more. There are now nice measurements and satellites using gravitational anomalies. Changes in the acceleration due to gravity have become sensitive enough that you can actually see the loss of mass due to glaciers melting in Greenland and Antarctica. You can see the loss of mass of water tables that are being depleted. And hopefully in the next version of these satellites, you'll get about a 2 more order of magnitude increase in the sensitivity in the spatial sensitivity and resolution. So rather than talking about climate models, I'm going to take a very epidemiological point of view and just say, well, what's really been happening? But I'm not going to use data from environmentalists or climate people. I'm rather going to use data from reinsurance companies. Now, why am I doing this? Well, because I'm trying, as others are trying to convince businesses that things are happening and it costs money. And so the insurance companies, in particular the reinsurance companies, are very, very mindful of this. Because what's a reinsurance company, you may ask? Those are insurance companies that insure insurance companies. So if you're an insurance company and there's a big disaster, you might not have enough cash balance to pay out the premiums. So you actually buy insurance for that. And so this is some data taken by Munich Re from 1980 to 2012 and part of 2013. And you keep track of earthquakes and storms and floods and droughts and forest fires. And this is a plot of just events that trigger insurance losses. It's actually a good metric because if you say, well, I'm only going to plot hurricanes above a certain magnitude, that might be misleading. For example, Hurricane Sandy, which is the last very big, devastating hurricane in the United States, wasn't actually a hurricane when it hit land. It was only a tropical storm. And yet, because it was so massive and because it was slow moving, it just dumped a lot of water in places you wish it wouldn't have dumped it. And so there were a lot of, in the New York metropolitan area, that and the high tides, it really devastated lower Manhattan, Queens, New Jersey. So these are just insurance losses, things that trigger insurance losses. Now, if you look at what actually happens in terms of the amount of loss, the dark blue are insured losses, the light green are uninsured losses. And the trend, again, very noisy, but the trend line is 40 billion for just US losses, going to 200 billion. But if you scratch below this number, you find that many of the things that you would normally consider as losses are not tabulated. Let me give you a couple of examples. If you're in a small business in, let's say, Hoboken, New Jersey, and you get flooded and your door's closed for a couple of months, and you might not have enough insurance to rebuild properly, you may go out of business. And about 20% of the little small mom and pop stores really crashed. When you go out of business, that's not an insurance loss. You just happen to be unemployed, but it's not an insurance loss. When you want to weatherize Manhattan, as they are going to be doing for Lower Manhattan, both the subway system and the electrical system, where the initial estimate is about $10 billion. It's going to be more. But that's not an insurance loss. That's called adaptation. In New Orleans, after Hurricane Katrina, we're raising the height of the levees. That's another $10 billion. Again, it's not an insurance loss. So 10 billion here, 10 billion there, and it begins to add up. Then finally, in flood insurance in the United States, there was a law that backstopped the insurance companies, that the federal government, if the insurance companies couldn't pay out for the premiums, the federal government, as part of backstopping, would step in and pay the premiums. And what happened after Katrina, but then in subsequent hurricanes, the premiums could never catch up with the debt of the insurance. So the insurance companies couldn't pay back this. And right now, it's a $26 billion debt that is not, and it's part of our national debt, and it's not, and once it's part of our national debt, well, it's part of our national debt. And so then as the cost of money changes or whatever, the taxpayers just pay for this, okay? And it's going up, not down. So these, again, are not tabulated as insurance losses, but it's real money. And so these things are happening. If the Munich Re looked at the biggest insurance losses since 1950, this is a 63-year period. 3 of them were earthquakes in New Zealand, in Los Angeles, and in Japan. The rest are storms. But look at the dates. 6 out of the 7 of these weather events occurred very recently, in the last 8 years. So the take-home message is, even though the climate people can't predict hurricanes or hurricane seasons or tornadoes, something weird is happening, okay? It's just epidemiology. Something weird is happening. So let's talk about some more epidemiology. This has to do with smoking. Smoking in the United States from 1900 to 2005. And we were not a smoking country in 1900. This is the average number of cigarettes consumed per capita per year. But by 1960, 1965, we're at 4,000 to 4,500 cigarettes on average per, let's say, American male adult over here. This blue line is deaths from lung cancer in males, adults in the United States. So that's quite remarkable. And by 1964, the science had gotten convincing enough, the epidemiology got convincing enough that the Surgeon General was able to put on the package of cigarettes warning labels saying smoking may be hazardous to your health. And subsequently, as the evidence mounted, it got stronger and stronger, and advertising in TV, advertising in magazines, forbidding minors to buy cigarettes started to happen. The cigarette consumption went down, and then the deaths in lung cancer went down, but not because of modern medicine, because the incidence of lung cancer went down proportionally. So there was a 25-year delay between, on average, when you started smoking and when you would have an onset of cancer, or in this case, a death, but that was a couple of years. During this whole time, in the 50s and 60s and even in the 70s, the tobacco industry wanted to muddy the waters. And they said, well, look, there's no real microscopic biological understanding of how cigarette smoking causes cancer. There's no real proof. So there's, what's the problem? Why don't we be sure about this before we have warning labels? And yet, this was happening. Well, 25-year delay didn't help. So in terms of analogy to climate change, we don't have a 25-year delay. In fact, we don't know what the real delay time is. but it's estimated to be at least several hundred years. So wait a minute, several hundred years from what? Well, 700 years from the time we've already put up a certain amount of greenhouse gases, carbon dioxide, to the time where you reach a new equilibrium. Why does it take so long? Because the ocean mixing time is very, very slow. It takes a long time for the oceans, the deep oceans, to warm up. In 2010, I spent several months commuting back and forth between DC and Houston, trying to help BP stop this oil leak. And during the summer of 2010, the surface temperature of the Gulf of Mexico was about 86 degrees Fahrenheit. The temperature where the oil was leaking out 1 mile below was 2 degrees above freezing. It doesn't change. The slow mixing time a mile deep is very, very long. And so you have, imagine you have more greenhouse gases, and imagine, we don't know this for sure, but we know over the last 35 years, apart from the 11-year solar cycle, the amount of energy instant in the upper atmosphere, in visible light, in infrared light, in ions, sunspots, microwave radiations, now being monitored by satellite, is constant. It's a constant baseline. There's a 11-year solar cycle. And during that time, there's less energy leaving the Earth because of the greenhouse gas effect. So the infrared radiation is being blocked, of some of it. And so because of that, over a long period of time, even though it's very complicated dynamics between the atmosphere, the oceans, and the biosphere, and how that all reacts, over 50 and certainly 100 years, it becomes less that, more conservation of energy. So this is the issue, but it's as though we're saying to ourselves as a society, well, we're really not sure the climate's really changing. There might be early signs, but let's wait and be sure. And until we're sure, why do we have to sacrifice anything or a different lifestyle or pay, you know, 0.5% of the GDP or 1/4% or whatever to do something about it? So it's this, now, you would probably never do this if you had grandchildren and you were smoking and you're puffing away saying, I'm not really sure, you know, yes, there's a 25 times more likely chance to get lung cancer, but it's not you, it's your grandchildren. So you're puffing away, but it's okay, it's my grandchildren. You would never do that. And yet as a society, that's what we're doing. There is no prediction of whether you get lung cancer or not. It just happens to be 25 times greater. And there's a 2 to 4 times greater chance you have heart disease and high blood pressure, statistically. So these are not small changes. These are big risk changes, okay? And yet as a society, not a worry, unless you're really sure, why, let's just carry on the way we're doing it. At least that's the dialogue in the United States for half the population. So this is an issue that this is the reason I took a 10-year sabbatical from science, or really only about 5 years. But so there are different scenarios as to what will happen, but I stress to you that these scenarios in IPCC stop at 2100, but most of the damage is not at 2100 because the equilibrium time is a couple hundred years. So the damage we've done up to since the beginning of the Industrial Revolution will be finally felt its entirety over here. And so that's the crazy thing. Now, this scenario, this very aggressive carbon control scenario is, sadly, I don't think we're gonna do this. We're gonna sail through 500 parts per million CO2. We're gonna go through 550 parts per million. And where we end up, I don't know. But if it ends up in this bunches of the degrees centigrade change, then it's, again, the physics technical term is you're in deep doo-doo. And so there's a very famous saying that the great American philosopher Yogi Berra should have said, but I don't think he said it. But if we don't change direction, we'll end up where we're heading. So this is indeed an issue. I apologize for the fine print, but But the remarkable thing is many of the large companies, including large multinational fossil fuel companies, oil and gas, actually recognize that the climate's changing. And they carry on their books, Royal Dutch Shell taxes itself internally $40 a ton of carbon dioxide. So when it starts to want to invest in this and that at tens of billions of dollars, it's saying, we know eventually there's going to be a price on carbon, and right now we have an internal price of $40 a ton. ExxonMobil has a stepwise thing, but by 2030, their internal accounting of how they make investments is going to be $60 a ton by 2030. And hopefully, the world will have a price on carbon sooner rather than later. I am getting more and more optimistic that China will put a price on carbon internally by itself. Forget about Kyoto agreements, anything else like that, in this government. That which means in the next 8 years. Because the people in China are saying this is happening, and the industries believe that the Chinese government, the central government, will put a price on carbon. And so Europe is certainly doing all these very nice things, and so the only big significant player who should be doing something is the United States, and hopefully it's not going to happen at the end of this administration, but hopefully in the beginning of the next administration, something will happen. Because it's an economic thing, and large companies, including oil companies, are beginning to say, this is happening. And that's an important change from 5 and 10 years ago. Okay, so here's part of the problem. You might say, well, we're going to run out of fossil fuel, especially oil and gas, and then it will be self-correcting. But here's where I quote one of my favorite authors, and our ability to find and extract fossil fuels continues to improve, and economically recoverable reservoirs around the world are likely to keep pace with rising demand for decades. So I said that. And so what was the reason why I was saying that? This is your typical peak oil graph, 1945 to 2009 U.S. oil production, and in the around 1970 we peaked in oil production. Even with the big Alaskan find, it still couldn't keep that slide. But then all of a sudden, in this little thing called tight, where you have tight oil and hydraulic fracturing and horizontal drilling, and so that began to change things. And by the end of 2013, the production in the United States went up about 1.5 million barrels a day. And by the end of 2014, it's projected to go up another 1 million barrels a day. That's significant. 2.5 million barrels a day is like all the oil production of Iraq or Iran. That's the increase. And it's projected to go up perhaps another 1 million barrels a day beyond that. So we are the second largest oil producer in the world behind Saudi Arabia, and we may, at least for a short period of time, pass Saudi Arabia. So this is economically recoverable oil at $80 to $100 a barrel. You can get at this. Natural gas. This is, again, 1945 to 2000 and projections to 2020. There's a consulting group that prides itself on its ability to project fossil fuel productions and prices and things of that nature. And so in 2000, I think it's in 2008, it lent this prediction that the natural gas production in the United States would go down, but what happened is it went up, and it's up here. And it's only when the price went below $4 an MMBTU, I think in England it's what, $12, $15, and for the same quantity of gas. And so the price in the United States is very, very inexpensive. It doesn't ship like oil, but there's where it is today. The amount of reservoirs around the world, potential reservoirs of tight oil and gas, are large. Roughly, again, it's just an estimate, but roughly an order of magnitude more than the United States. Whether this comes to pass or not, we don't know, but it will really change the dynamics. That's tight oil like shale, shale gas. Then there's heavy oil, bitumen oil that's like just essentially like tar. These are, for example, oil sands, or very, very heavy oils that are nearly solid, very, very viscous. Again, at $80, $90, $100 a barrel, technology has found out how to extract this profitably. And this is the estimate of how the world parses out to what the conventional oil, West Texas crude, Saudi Arabia, Middle East oil, that's up here. This is the Venezuelan, very heavy oil, the tar sands oil, things like that. So most of the oil is really heavy and taking 20 to 40% more energy to extract and refine. But economically, it's possible. So this is what we're facing. So there's another famous quote I always try to remember, and that the Stone Age came to an end, not for the lack of stones, and the oil age will come to an end, not for the lack of oil. Now, remarkably, this was said by a former Saudi oil minister, and I don't think that's why he's former. And so what's unspoken in this is that when we went from the Stone Age to the Copper or the Bronze Age, we transitioned to better solutions. So what's a better solution? A better solution is energy, clean energy, but economically competitive energy. Okay? If it costs twice as much, it's going to be hard for a lot of, especially developing countries, to embrace this. So let me talk briefly about some pathways. Some of it's small-time stuff, but it all is necessary. And I'm a big fan of energy efficiency. And in energy efficiency, this is appliances, and this is an experience curve. When you double production, you double production, you double production, then the price of this appliance, a refrigerator, in red, goes down by a certain fraction. Let's say every time you double price, it goes from here to here, so it's gone down, I don't know, in half. So that's why on a log plot, you have a straight line. So many technologies follow experience curves. So this red line is appliance, the cost of a refrigerator of a certain size, and 18 cubic feet, where you try to make adjustments, because back here in the early days, in the 50s, there were very few 18 cubic foot refrigerators, and nowadays in America, there are very few 18 cubic foot refrigerators. The size of the American appetite is somewhat unbounded. But in any case, this is before appliance standards, and then in 1975, was the first appliance standard in California, but because California is such a big market, it had an impact on US production. And there were 3 California standards followed by 3 federal standards. And this blue is the cost of ownership. That's the purchase price and the cost of energy. And so this is a bunch of physicists who are taking, we are predisposed to taking data as physicists. And so we said, well, in terms of efficiency standards, do appliance standards actually increase the cost of the appliance? So it was expected it would increase the cost, and as you see, oops, the cost didn't increase. It followed the same slope. Of course, the cost of ownership went way down. This is a log plot, and so you would have been over here. So it really dropped, the cost of ownership dropped to 1/3. That was a big deal. Then we looked at room air conditioners. Before standards, after standards, here you see the dates. The first standard is 1979. And what we did as physicists is we said, well, look, we'll use a computer to test something. If you see a change in slope, the data tells where the change in slope is and what the 2 values are. And remarkably, coincident with the time of standards, you see something quite unexpected. The purchase price went down faster than before standards. So you could theorize about why that is. It could be that you're making a more efficient compressor, therefore you can make a smaller compressor, you change the duty cycle, so you're right-sizing the compressor, all these things. That all helps in efficiency. That's room air conditioners. We looked at washing machines, and we looked at central air conditioning. We saw the same thing. And then we looked at, and we chose those appliances because they had the longest historical record. And then we looked in Europe. They didn't have standards. They had grades of appliance efficiency, but the same progress. Remarkably, if the engineers say, this is what you have to engineer to, they get better and better at it. And it doesn't show up. Okay. So, but you need the standards in order to nudge them to do this. This is actually a bit of a market failure because you could say, how could it possibly be that the engineers wouldn't design something better and cheaper? You needed a standards to do that. But in any case, we got excited, submitted this to science, and one of the referees said, this is amazing, we should change our thinking about it. And the other two were more sanguine, and one was completely hostile and said, it doesn't matter what these authors say, the economists are not going to believe it. Which, well, okay, so I'm not an economist. Partly because we are partial to data. So in any case, that's very snide, I'm sorry. To all the economists in the room. So here's another example of how standards are really needed, and without standards, there's no market pressure to do the right thing. So when I was in Secretary of Energy, I knew that if you have cable TV or satellite TV, you have these little set tops that sit on top of your TV. And it takes the digital signal, decodes it, and it gives you your TV signal. And in the United States, this has become a big deal. There's lots of homeowners. There are 90 million subscribers of satellite or cable TV. That's a lot of, and then you get 4 of these things, just typically. And if you plug them in, I don't know how many people have these set-top boxes in their homes, show of hands. Okay, you notice that they're kind of warm? At least, I don't know the ones in Great Britain. The ones in the United States, you put your hand on it, and if you have it behind a cabinet, it's toasty warm inside there. And so I was disturbed by this because they were dissipating between 30 and 50 watts per box. Okay? Your refrigerator, a good modern 18 cubic foot refrigerator consumes 40 watts, time average. So one of those boxes is equal to 1 refrigerator. But if you've got 3 of them, you've got 3 other refrigerators going. It's about 30% of our electricity bill. How do I know this? Because when we go away for a week, we turn off the heat, we turn off everything. We're not cooking, we're not lighting, and then it baselines to this level. Very scary. I have to do the eventual experiment, unplug all the box tops, and to see what happens. But that's the only big drain. All right. So I was Secretary of Energy. I wanted to put some regulations on this. And 6 months after I leave office, I see this big announcement saying how proud they are to announce that instead of a regulation, they agreed on a voluntary measures, which is what industry wants. And in this press release, they say that you can improve the box top efficiency by 10 to 45% by 1917. Now, so my head of public affairs, former head, he emails me, he must be very proud of this, and I wrote back, no, I'm devastated. This is terrible. Why was I devastated? Well, you have to ask the question, not will industry agree to, but how hard it would be for them to engineer something much more efficient. So the dark secret is when you turn it off, you don't turn off anything except the LED display. The innards are still on, and if you happen to have a hard disk recorder, they keep the hard disk spinning. They just leave everything on. Now, they claim they want to leave everything on because it has to download programming information. And it takes about 5-7 minutes to download this programming information. And for that reason, you will not unplug it, because when you want to watch the television, you don't want to wait 7 minutes for it to say, wait, I'm reprogramming. Okay? So what can you do? Well, you can have a little chip that has a quartz oscillator, and it wakes itself up at 3 a.m. in the morning and downloads programming information, puts it into memory. 100 kilobytes will get you a week's worth of information. And I don't even know how to price 100 kilobytes of memory. It's just like, it's too free. The power of the quartz oscillator is just too low to think about because it's like your wristwatch. A little battery goes for 5 years. Okay? So then you can turn off all the electronics. And I thought you could go down to 1 or 2 watts instead of 30 or 40 watts, but I was wrong because it turned out that in these internet TV thingies, they have standby power not of 1 or 3 watts, but they actually, some of them have standby power of 100 milliwatts. Okay? So you go from 30 watts to, let's say on the high side, a watt. It's 30 times less energy. Well, so now, why didn't the companies want to do this? First, they reuse the electronics. That's another secret. They actually put the old cards into new boxes so that the consumers think they're getting something new, and they even put in new serial numbers. And because I looked for what the power usage of the box we have, and I couldn't find it, and then I found it in Google. It says, oh, no, that's not the serial number. That's the fake serial number. Look underneath in the paper sticker. That's the real serial number. So as long as they're not paying for the electricity bill, it's OK. How much is the electricity? Well, in the United States, now our electricity is pretty inexpensive. Average, it's 15 cents a kilowatt hour. I don't know, yours is about 25, I'm guessing, okay? And if you got 3 of those boxes at 15 cents a kilowatt hour, you're talking about $130 a year, just for electricity. You multiply by 90 million customers, you're talking $12 million of money. You're talking 10 nuclear power plants at 1 gigawatt apiece to keep those box tops running. Okay? It's kind of gross. There is no reason why we shouldn't be at a fraction of a watt. And it's a regulation. It's just the regulation for the power supplies of this is a power supply for my computer, and it's not a very efficient converter, and it's pretty warm. You can make it 90% efficient, or you can make it 50% efficient, and you save, I don't know, pennies by going to 50% efficiency. Okay? So there's a lot of this stuff going on that one has to, and any new electronic gadget, very quickly, the regulators have to catch up and do this. So there's other things we like and care about, like a mobile wireless. And if right now the electricity bill for wireless is about, in the United States, is about 2% of our electricity. But it could go to 15 and maybe even over 20% if you just follow the natural technological development. So you have to go out of your way to actually make it more efficient. And it's surprising. In California, we use over 20% of our electricity to pump water. And as the weather conditions change, we use more of it to pump water. The wells go deeper, and there are more aqueduct systems and all this other stuff. So this is, again, these are big deals. And so you need to look everywhere. Now, clean energy sources. The good news is they're getting less expensive. In the United States, good wind sites are down to, this is the levelized cost of energy to construct a turbine in reasonably good wind sites, not the best ones. It's about 7.5 cents a kilowatt hour. And people are signing power purchase agreements. They can, at a profit, of 10, 11 cents a kilowatt hour to sell in a 20, 25-year contract with profit and cost of financing and everything else like that. And it's going to continue to go down. And so as they become more reliable, as the towers go higher, in the United States is very good because we have a lot of very good wind resources where there are not very many people there. That's the good news, and the bad news is there are not very many people there, so you need transmission lines, and then there's this perennial fight about transmission lines. But they're going down in price, and what's going to happen is that probably within a decade, 2 decades at the outside, including transmission, wind will be less than natural gas, even if natural gas is still below $6 an MMBTU. Still half the price in Europe. So, it's catching up. Solar is also making great strides. Again, a learning curve of crystalline solar and thin film solar. And this is an order of magnitude drop in price. And so you see there were, again, a learning curve and the price dropping down. The price dropped precipitously down due to overproduction and then a recession. It's popped back up, but it's now leveling out, and that bulge in production is working its way out of the system and is projected still to decline. So what happened in the last, let's say, 10 years is the cost of solar modules, the cells plus the wiring, the packaging, everything, dropped more than fivefold, okay, in price. So imagine a $30,000 car, all of a sudden the comparable equipped performance car costs $5,000. Okay, it's really dropped. It's dropped so much that the total cost of solar is not the cost of the module, it's the cost of installation and hookup and licensing and inspections and things like that. So right now, the production costs are about 50 cents a watt. They're selling for about 80 cents, 90 cents a watt. Okay, so this is amazing. But in the last 2 years in the Department of Energy, as we noted that this technology headroom is still there, still continuing, where do we want to spend the taxpayer money? And we started to shift from we still fund very basic research for really better ways of doing it, because if you can get the efficiency from 20%, well, it's now about 16, 17% for crystalline. It's going to go to 20%. But if you can go from 20 to 40%, then all the other associated costs go down as well. But aside from that, we started to shift towards what are called soft costs, and that's the installation. Why is there a big licensing fee, things of that nature. And the head of the current so-called Sunshot, it's named after like moonshot, but for solar energy, the head of the program said, unlike physics where we can fundamentally figure out the upper limit for the efficiency of solar cells, there's no such limit to bureaucracy. And remarkably, in the United States, many municipalities charge large fees of thousands of dollars, $1,000 or more, because it's part of their income enhancement. And we're trying to convince them, make your money in parking tickets and speed traps. Don't make your money on charging for fees and installing solar. But nevertheless, we're doing this. And in Germany, for the same size solar module, remember it's an international price, it costs about $2.50 for a certain generating capacity. And in the United States, it costs $5. And of course, it's because German labor is cheaper. Not. So the Department of Energy actually started filming people installing stuff on rooftops and find out that Germans spent 1/3 of the time on the roof. Okay, and it's not like they're in a high-speed motion picture camera of what's going on. Okay, they just get efficient. If you think of an efficient plumber compared to when you try to do the plumbing yourself, it's an all-day adventure. If you do it and the plumber does it in 20 minutes, well, of course they have the right tools. But, but seriously, this is something the Americans can learn. This is not high technology, but it is an important part of pricing. And so, you can make a water heater, get it installed very, very quickly and efficiently, whether it's a normal or a tankless. So anyway. Now, I wanted to tell you a little bit about a new agency we started in the Department of Energy called Advanced Research Projects Agency for Energy. It was modeled after DARPA, which is a really aggressive way of funding out-of-the-box research. We did not want incremental improvements. We're not looking for 10, 20, 30% improvement. We're looking for 2x, 3x, 5x improvement. Now, when you look for that much improvement, there's a chance you will fail. But unlike most government funding, where the people funding get a little scared, they want to have big success stories, or they just want to have success stories, and so they like to fund more sure bets. But we weren't interested in those things because once it gets to be incremental, industry should be taking that over. So we wanted to use an American baseball analogy. We wanted people to swing from the heels and to hit game-changing home runs, not infield singles. But you're going to strike out more. So now, here's the rub. How do you tell what you're going to fund, whether it's just a crazy, stupid idea that violates the second law of thermodynamics, or it might have a shot? In order to do that, because it's new, you have to have extraordinarily good people. Once it becomes fashionable, peer review helps. but before it becomes fashionable, peer review does not help. Okay? And it's sad, but true. And so I was part of this committee in 2005 that wrote a report called Rising Above the Gathering Storm, which is how does the United States can survive in a flat global economy? And the answer was very easy. It's pay attention to your intellectual capital, both in education and science and technology education, but in nurturing science and technology jobs. And we didn't talk about any specific science or technology except one, energy. And in that report, we said, because energy is going to be such a central part of the future economy of the world, and because we need new forms of energy, we said, why don't we form something like this, modeled after DARPA, to actually get it going. And then, so that came out in 2005. I was a member of the committee. There were 20 people on the committee. And I was sent to Congress as representing the National Academies of Science and Engineering in the US to try to sell it to Congress. And in the hearing in Congress, they had other people trying to argue against it. But in the end, after 2.5 hours, the strong consensus was, if you get the right people, it could work. If you get the wrong people, no matter what organizational structure, it will fail. Okay, so then I was sent, and so the House committee did the authorization, which allowed it to be in the budget if you ever found the money. And then I was sent to the Department of Energy to try to convince the then Secretary of Energy, Sam Bodmer, a very good guy. Could he support it? He wanted to support it, but some of his career people in the Department of Energy said, no, you don't want to do this because it could be mistaken for basic research, and we don't want this to crowd out basic research, because it was daring applied research. And so they didn't support it. And it wasn't until the new Secretary of Energy came in 2009 that it found a sympathetic ear. And so that's what happened. Let me give you one small example of some of the things. It was not set up as a passive agency that would just accept proposals. It would actually look and say, are there any areas in technology that could benefit from a little nudge in money? One of the areas in technology was high power electronics at also high frequency. And if you look at power electronics at low frequency, like 60 hertz, you can have reasonably high power. But if you're using silicon as the base semiconductor technology, as you go to higher and higher frequencies, it goes to lower and lower power. And so we said, well, what if you use different materials? In particular, if you use large band gap materials like silicon carbide and gallium nitride. And in gallium nitride, it was a materials growth problem of high enough purity. So we said, we're going to do that. We're going to look for things like that. Silicon carbide, you had a little bit of stuff, but then we nudged along those lines. And within 2 years, a company, Cree, that makes LEDs, made a silicon carbide transistor that's a megawatt at tens of kilohertz, the size of your fingernail. Okay, now it's expensive and it's a prototype, but it's a start. Because when you go from 60 hertz or 50 hertz to 50 kilohertz, roughly the transformer size roughly goes inversely like the frequency. So a 77,000 pound transformer at 60 hertz becomes 150 pounds. And the last year I was in the Department of Energy, a company had a little prototype transformer that fit in the back of a trunk that he could actually pick up in a suitcase. He was a strong guy and could walk it over and say, here it is, here's a transformer. So it was a good start. And so this is what was happening. And we also were investing in very, very novel batteries to get batteries to the size of the cost of pumped hydro, where you don't have pumped hydro everywhere in the world, and those you can put in a lot of places. So, batteries have been making dramatic improvements. 2008, the cost is manufacturing cost is $1,000 per kilowatt hour of usable battery. By 2012, it dropped in half. We set a very ambitious target to drop it another factor of 3 by 2022. Now, whether we get to this or not, we don't know. There's a lot of exciting approaches of solid lithium anodes, lithium sulfide, metal air batteries. Many of these will not work. Some of them might work. But we are looking for a factor 3 or 4 drop in price, 4 drop in price for an automobile battery, and at least a doubling, perhaps a tripling of energy density. The limits of battery energy density are we have metal air batteries that are about 10 times higher energy density, but not rechargeable. So at least there's an existence proof of chemical storage that can be high energy. But still, it's not rechargeable. There's a couple of companies now building prototypes in this sort of dollar range. And this particular company is claiming at least that they have maybe a 30-year lifetime. So whether they do or not, we don't know. The old Mark Twain comment about there's liars, they're damn liars, and there's statisticians. And that's true of battery people. So there's lots of claims of batteries, but I think you have to be optimistic if you're in the battery business. But I'm hopeful that some of these things will come to pass. It doesn't always have to be batteries. You have to think in the good old days when energy wasn't cheap and you can just flick a switch. You used energy when you had it to do certain things. For example, when the wind blew, you pumped water. Okay? We have to get back into this mode. When the renewable energy is blowing or the sun is shining, use the things you can do it. And high energy intensity factories, you might as well use them at night or whenever wind blows. And if they're automated, you don't have to do it during the day. And so you have to get, so that's a form of use the energy when it's cheap. And by the way, this is an amazing economic insight. In the United States, I don't know what it is in Great Britain, but in the United States, the cost of energy during the day, especially in the summer and at night, is 3-fold different. Could be 4-fold different. Because we're shifting to time of day pricing. How much does it really cost? And if electricity is 3 times cheaper at night, if there's an automated process that's energy intensive, do it at night. Okay? If not, do it all the time. And then you can actually adjust a hot water heater, especially a large one, this is a residential one, to go up and down by, let's say, 4 or 5 degrees C. To be, it gets to be significant energy storage when multiplied by a lot of water heaters. And then a trivial technology then says you get to not scald yourself by just having a temperature sensor as the water comes out to do a little premixing with cold water. Again, remember, electronics and actuators are very inexpensive. And so this becomes energy storage, but it's a different energy storage. So what we started in the Department of Energy is much more try to get more innovative stuff, be more daring. That means you have to bring in lots of very good people. I was quite proud of the fact that we brought in a number of extraordinarily good people. 6 members of the National Academy of Sciences and Engineering came to work. Some of them elected in their 40s, but they were still in their 40s. So what would induce someone who's elected, let's say, in the National Academy of Engineering in their middle 40s to put their career on hold for 3 years to work for the government? And what would induce them is because we need those type of people. And we have a lot of others who I think will be in the National Academy in not too distant future, because they were that quality people. So they were the quality people that can make the right funding calls and can separate the snake oil from the good stuff. And then you just have to make sure that they're instilled with, shoot for the moon and the sun. And again, there's a famous quote, not by me: "The greater danger of most of us lies not in setting our aim too high and falling short, but in setting our aim too low and achieving our mark." And so that was said by Michelangelo. And this is something that when I am and was a professor, this is what was my mantra to them. You're encouraged to fail, but fail quickly and move on, and it wouldn't be a black mark against you. Because you get to try lots of things, but try them quickly and move on. All right. So now, today there are 7 billion people in the world, and by 2025 we're going to go to 8 billion. And by mid-century we're probably going to be 9 billion. So you might ask, you're just postponing the inevitable. The inevitable is that we're going to be in a very non-sustainable world because of population. And in that population, growing population, there's also an expectation of higher standards of living. The good news is that for the first time ever in my lifetime, certainly, it's now being projected, perhaps the median fertility rate, by the end of this century, the population may peak at 10 billion and then start to decline. And it's because across all cultures, across all religions, across everything, richer people have fewer children. There's no expected infant mortality. There's all sorts of other issues. There's women's education. There's nighttime TV. There's all sorts of reasons why richer people have fewer kids. I'm not kidding. If in blackouts and there's nothing else to do, there was a little baby bulge in New York City, Northeast blackout. In northern climates, anyway. Without getting into particulars, there's some hope. But let me also say that there's something else very fundamental, and that is that the world economies have to learn to have a standard, even rising standard of living, without growth of population. Okay? Because the growth of population is a mild Ponzi scheme. Okay? If you think about it. So it's easier to have a growing economy if you have a growing population. Okay? But if you have a static population, it's harder, and it really becomes to get harder if you have a shrinking population. So this is something we have to come to grips with. The myth about the fact that energy consumption is directly proportional to prosperity is overstated. That's why I call it a myth. This happens to be electricity consumption, not plotted in GDP per capita, but in GDP per capita plus education, average education plus average healthcare. And Norway and Iceland are outliers because they have hydropower, and electricity for them is essentially free, so they heat, they do everything with electricity. But there's a big clustering of wealthy countries over here where it plateaus. Down here in developing countries, when you're really down here and you're using a couple hundred watts a day or less, energy is proportional to prosperity. But once you're up here, it's not. And so the question is, can you use it much more efficiently? And Europe wants to be over here, and if Europe wants to be over here, certainly we should be able to do that as well. And so this is the issue, because that is absolutely needed in order to create the headroom. This is another plot of, it's a sustainability plot that you have to take with a grain of salt, because this is how many square feet of earth does it need in order to maintain a certain standard of living. Here's the US way out here. We eat a lot of meat. That uses a lot of land use. We drive big, heavy cars, all sorts of other things. And so we're big on the ecological footprint. And here again, how do you get down from there? And whether I think it is possible to get down here without denting the standard of living, again, for technological headroom. But let me also say this. We don't really know how much the Earth can sustain. Because remember, this green revolution is 4 times greater agriculture per acre of land. So we're not sure where this line is. We know that we can certainly move over here, and whether we can move it over here in a completely sustainable way remains to be seen, but to me, this is a science and technology issue, and it's a very important one, because the limits of sustainability are not known. I do know not every person in the world can own a Gulfstream jet, but now, some friends ask me, because there's a lot of bad stuff that you have to put up with as Secretary of Energy, and would I agree to do this? And the answer is, in all honesty, yes. A lot of the really best stuff is hidden under the radar screen. It's getting really good people and making better funding decisions and things like that. And in hindsight, probably the best thing I did was to get on the phone and actually get some really good people I know, not only at the immediate levels, but 4, 5, 6, 7 levels down. And so if the Secretary of Energy calls up someone and he says, come join me. You can actually get some of them to take a big hit in salary and put their career on hold for a couple of years. But in the end, I don't think it really damaged their career, because it gave them a view of the world and an experience that actually helped shape what they were doing in the future. So, and then you block and tackle, and you don't let the bureaucracy drag them down. So that's also something very important, because when you have someone who starts to work 70 hours a week, which is what these people were doing, a lot of the old-time government don't like that. Are you trying to make us look bad? And so you really have to do a lot of active protection. And you get enough of them within a little subsection to do that, and it changes the mood. And so it was happening little by little. So in mid-November of 2012, the president, after his reelection, and then a week later he gets back to work, and so he wants to know what's happening, and I was, for other reasons, first online, and said, Mr. President, I really love working for you, but my wife continues to impress upon me that no one's irreplaceable, and it's time to head back to California, and I'm going back to California. So I said, okay, you're right, I'm coming too. And so in February, I was allowed to tell people I was leaving. And in February 7, The Onion publishes this article, and it says, hungover energy secretary wakes up next to solar panel. And it goes on to say, sources have reported, following a long night of carousing in a series of DC watering holes, Energy Secretary Steven Chu awoke Thursday morning to find himself sleeping next to a giant solar panel he met the previous evening, alleging that I didn't even remember the manufacturer's name. And according to sources, Chu's encounter with the crystalline silicon solar receptor was his most regrettable dalliance since 2009, when an extended fling with a 90-foot wind turbine nearly ended his marriage. So I go into work February 7, and my public affairs guy is kind of smiling. He says, we have to answer this. You just can't let this. And so we issued a press release by noon that said, I just want everyone to know that my decision not to serve as second term as Energy Secretary has absolutely nothing to do with the allegations made in this week's edition of The Onion. Well, I'm not going to confirm or deny the charges specifically. I will say that clean, renewable solar power is a growing source of U.S. jobs and is becoming more and more affordable. So it's no surprise that lots of Americans are falling in love with solar. And he refused to let me put in regardless of your sexual inclination. Now, I should say that during this crisis, my wife stood behind me. And what she really said was, you don't have hair on your chest. So that was good that they did a very bad job of photoshopping. So I go back to the first slide, which shows this one of my favorite pictures. This is Earthrise, the Apollo 8 mission, the first one to orbit the moon. And the last orbit, they turned the capsule earthbound, and the astronaut took a picture of Earth next to the lunar landscape. And the astronaut who took this picture said, "We came all this way to explore the moon. The most important thing is we discovered the Earth." Now, since that time, we've discovered that the destiny of the Earth seems to be changing, that it's due to humans. And so I want you to look at this and say that this is not a good place to live. This looks much better, at least from this vantage point, and there's nowhere else to go. And so this is one of the things, but I know I've been talking a long time, but I just want to finish by telling you of even a more distant view of the Earth. This was taken by Voyager 1, which was the first of the near flybys that was launched in the 70s. And when Voyager 1 was leaving the orbit, if you will, of Pluto, Carl Sagan convinced the NASA engineers to turn the satellite backwards to take a picture of Earth. Now, this satellite was designed to take nearby pictures of Saturn and Jupiter and Uranus and all these other planets. And so it wasn't designed for a long-range picture of the Earth. And so this is a narration of Carl Sagan as to what they saw.
From this distant vantage point, the Earth might not seem of any particular interest. But for us, it's different. Consider again that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust, suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
Okay, thank you.